Mhm. Okay. Okay, good morning, good afternoon, sorry. Good afternoon, everybody. We're starting our afternoon session of Algebra 3 in Natal, and it's a very special occasion today because we are doing live event also together with our lead JOR seminar in Sao Paulo. So we have, I believe there are plenty of people who will join us there on our transmission on YouTube. And it's kind of non-official, but we continue to celebrate Ivan's 75th birthday, although it's probably not the best. It's strange a little bit to start it with his own talk, but I believe it's also a very good way to and we had here like 5 years ago we had here in Natal his conference for his 70th birthday, and I believe it's very traditional already that Natal hosts events, or at least which are at least partially dedicated to Ivan Pavlovich Shestakov. So please welcome our first speaker, Ivan Pavlovich.
Thank you. That really I have very good recollection on Natal. It was a wonderful conference 5 years ago. Well, as Irina mentioned about the age, they say that person in old age often falls in childhood. So I will try, something like fall in my scientific childhood. I will return to some things which I was, initiated in about 50 years ago, something like that. Well, in 60s and 70s of the last century, there was quite popular to try to unificate of series of structure series of alternative and Jordan algebras. They have a similar, at least in finite dimension, they have similar, I would say, features, which in fact, like Wedderburn theory for associative algebra. This means that nil algebra, nilpotent, maybe. Nilpotent, every algebra A, I mean speaking about finite dimension now, has a nil radical. They are those alternative and Jordan algebra, they power associative, so nil radical is well defined, it is nilpotent, so a quotient algebra is a direct sum of simple algebras. The structure of simple algebras described, there is, and also there is a, I would say, a Wedderburn principal theorem that any algebra is a direct sum of the vector spaces of semi-simple part and nil radical. This was both alternative for Jordan algebra as well. These results were true. So there were attempts to unificate this theory in some bigger variety. Probably it was started even in Albert works, but the first result will be by Richard Schaeffer. he introduced so-called general standard algebras. They satisfy the same, all this theory was proved with this class of algebras. And much later, in fact, it was proved in the paper of Dorofeev that in fact, this general standard is just the union as varieties. So this is the minimal variety which contains both Jordan and alternative algebras. Then there were more generalizations by Richard Bloch and Armin Teddy. They introduce even bigger varieties, which are strictly bigger than general standard algebra, which still satisfies all these results. And all these varieties were contained in so-called non-commutative Jordan algebras. I will not give identities defining these varieties. What non-commutative Jordan algebras, yes, it's just two identities: flexibility and Jordan identity. Well, here it means associator, which means deviation from associativity. But this class is extremely large. For instance, you can see that every anti-commutative algebra satisfies this identity. So this class includes all anti-commutative algebras, and it's, of course, it's hopeless to construct a structure theory of this type, which include all anti-commutative algebras. Even for Lille algebras, for instance, this is not true. So it's too big for this. And even at that time, probably in 70s of the last century, I consider the class of non-commutative Jordan algebras, which satisfies this identity. This class includes both Bloch and Teddy and so all others, and satisfies all these, also these theorems, all of these theorems. But in general, if we recently I considered with my former student Vinicius Betancourt so-called non-matrix varieties generalization. Well, non-matrix varieties were introduced for associative algebras by Viktor Nikolaevich Latyshev. Varieties non-matrix is it doesn't contain matrix algebras, non-trivial matrix algebra for the two. And in attempt to generalize these varieties for non-associative case, but it would quite rather easy to extend this for alternative and Jordan algebras, and then looking for more general varieties. I realize that there is a more natural condition in unifying this Jordan or alternative theory. And namely, both in alternative and Jordan algebras, there is a theorem such that if A is alternative or Jordan, and it is nil of bounded degree, then A is locally nilpotent. Of course, this is without finite dimensional, just in general. Alternative for Jordan algebra, which is nil of bounded degree, is locally nilpotent. It is, in fact, in both varieties, it is just profound theorem, profound results. And for alternative algebras, it was proved by Shershov. And for Jordan algebras, it was proved by Zelmanov. And these results was, at least methods of the proofs was lately used him in proving a similar results for Engel and Lie algebras, and eventually he used these methods for solving the Berzite problem in finite group. In fact, methods were coming from here. So if you want a variety which contain journal and alternative algebra satisfies this theorem. What if you consider just this identity? This means anti-commutative algebras. So it's natural to assume that every anti-commutative algebra should be locally nilpotent. And it's exactly the condition which I introduce now. Well, this the variety V is locally admissible variety V. If any anti-commutative algebra from V is locally nilpotent. Locally nilpotent. Locally in parentheses because, well, maybe locally, I'm not here, locally. If you assume the variety, we will call it admissible. If any commutative algebra is this variety is just nilpotent. And in this case, the index of this nilpotency, it's natural to call it index of admissibility of variety. For example, well, variety of Jordan algebras is 2 admissible evidentially. Variety of associative algebras is 3 admissible. The variety of alternative algebras is 4 admissible. 4 admissible. Any anti-commutative algebra is nilpotent of degree 4, case degree 3, and so on and so on. And for instance, this variety, which I considered, it is locally admissible, but not admissible. So locally admissible and admissible, not the same. It is locally admissible, but not admissible. Not easy, not difficult to prove. So if you consider admissible varieties, locally admissible varieties, for them, many, well, not only finite dimensional, but some structure result for infinite dimensional algebras, it was possible to prove. Well, let me see here. For instance, well, to start with, I will need it to show, well, this result is true. Every nil algebra is nilpotent in admissible variety. Any semi-simple algebra is a direct sum of simple algebras. This is an open question, simple algebras, because it's too general definition to classify simple algebras, even finite dimension, it is not clear. And this also, it is not clear whether the Derburn theorem is true for any algebras in admissible varieties. But I will show what results can be proved. First of all, results about local nilpotency and local finiteness, also which related with so-called famous Kurosh problem. They both, I need the notion of local nilpotency and local finite dimensions is a partial cases of so-called locally finiteness in the sense of Shirshov, which was introduced in Shirshov. I think it's useful notion, so I will remind it. Let A be an algebra over a ring, associative commutative ring phi, with 1. Is Z be an ideal in phi? A finitely generated algebra A is called finite over Z if there exists some number m and some elements a1, an from A such that this is verificates. If z equal to 0, we will get local nilpotency. If this ideal is the whole phi, it will give locally finiteness. Locally finite. And many results can be proved in uniform way. Just consider this locally finiteness in the sense of Shirshov and proving the result. Well, in the first result, let V be a locally admissible variety. Then locally nilpotence in locally finiteness, sorry. Well, then locally finiteness in Shirshov sense is a radical property. Radical in the sense of Amitsur-Kurosh. This means that any algebra contains a maximal locally finite in this sense ideal. Well, algebra is called locally finite if every finitely dimensional subalgebra, finitely generated subalgebra is finite. So there exists a maximal locally finite ideal such that a quotient algebra has no locally finite ideals. Even more, it proved that a quotient algebra is approximated by prime algebras without locally finite ideals. Why? Well, sorry. I mean, when I is not finitely generated, I mean, well, in fact, in this case, for finitely generated, just nilpotent. Yes, yes. But if we can introduce the notion of locally finiteness, then it will be locally nilpotency and this locally finiteness. And this is well, second result, it's interesting that you see, if we consider anti-commutative algebra for admissible varieties, this means that, well, A is anti-commutative if and only if, in other ways, we can say the corresponding Jordan symmetric algebra, not, well, Jordan, because we consider it's non-commutative Jordan algebra. A is anti-commutative if and only if this is squared is 0. So one can prove the second result that A is nilpotent. Sorry. Locally nilpotent if and only if A plus is locally nilpotent. This means locally applied because when the variety is admissible, then just we have nilpotency. When the variety is not admissible but locally admissible, then I could prove only for this equivalence only for finite generated case, for finitely generated case. Depends whether the variety is admissible or no. If the variety admissible, then just nilpotency is equivalent, and if the variety is locally admissible, then that's. And using this result, it was possible to prove exactly. One can define a notion of polynomial identity in this variety, and if A is Pi and algebraic over Z. Z also ideal of ideal algebraicity. I mean, one can also be defined over the ideal. Then A is, well, locally admissible. Then when is it locally finite? Over Z. Over Z. This is means that Kaplansky or no Kurosh problem has a positive solution for pre-algebra in admissible varieties. In particular, this implies, well, of course, what can be proved easy, but that nil algebra, finite dimension nil algebra is nilpotent, for instance. It also much more. Well, now I will say about some open questions which appear here in this collection. The first interesting question well, about the concrete examples. The definition is just general, but a concrete example. The first example, if you consider this variety of non-commutative Jordan algebras with this identity, we don't know, is it locally admissible? It is equivalent to the following question. Let A be anti-commutative and 3 Engelian. Is A locally nilpotent? Anti-commutative 3 Engelian algebra, is it locally nilpotent? One can prove that finite dimensional algebras 3 Engelian are nilpotent, but finitely generated, it is an obvious, it is equivalent. In fact, even more, one can prove that not only finite dimensional, say, an algebra with maximal condition for subalgebras is nilpotent, but in general, we don't know. It's an interesting class because simple algebras in this class are classified. Let's denote by this. Finite dimensional simple algebra with, of course, with non-commutative Jordan. Well, everything I consider in a commutative Jordan is either Jordan, commutative, or alternative, or a certain 7-dimensional algebra. Seven-dimensional quadratic algebra, it's interesting algebra. It appeared in some cognitive physics. They call it the algebra of color. So it's simple 7-dimensional algebra, quadratic. It's quadratic algebra. Only one, except of alternative and Jordan. And we don't know, well, the Verburn theorem is not true for this class of algebra. Thinking about classification of simple algebras, of simple admissible algebras, the following problems appear. Well, open question, it's in a sense. It is known, one can prove that a very simple non-commutative algebra, non-commutative Jordan, in fact. For simple algebras, there are the following conditions. Maybe Jordan, well, not nil, simple, not nil. Jordan algebra, quasi-associative, third, quadratic, and the fourth is so-called Kokoris algebra. Well, Jordan, this in quasi-associative, I will not enter in details, they are admissible. This is admissible of index 2 and this is admissible of index 3, like associative. Excuse me? Sorry. It's an interesting question when a quadratic algebra is lies in an admissible variety. What kind of quadratic algebra? In particular, algebras obtained by a Kelly-Dixon process, they all are here. The simple quadratic algebra is flexible. We know that up to 3 algebras are admissible: associative, quaternion, octonions, it's an alternative condition. But what about, for instance, sedenions? Whether they're admissible or not? We don't know. Well, I'll have to check. Well, admissibility, in fact, is equivalent that there are a series of identities of something like this. Some say, a kind of liver breads, it's some homogeneous identities. That should be serious. In fact, well, any Lie product of n elements should be equal to some Jordan products, linear combinations here, Jordan products, I mean symmetric. So should be identities of this kind satisfy. Of course, the trivial example of admissible variety, just linear potency. You can put 0, it will be admissible. But it is not so interesting because it will not contain alternative associative, even associative. It will be, well, maybe interesting. There are simple algebras also. They include all Jordan algebras. Any nilpotency of this kind will give a variety which contains Jordan algebras. And there are simple algebras, for instance, even we consider only this, just nilpotency of index 3 already gives some new simple algebras. And if you consider here this angle of index 2, one can prove that will be admissible. And this, for any n, there exists a simple algebra of dimension L. So they are rich for simple algebras. But it's interesting, would be interesting to know what kind of when quadratic algebra. In fact, this quadratic algebras, their description, they reduce to the following. Any algebra of this from here has a the following form. It's direct sum. V has anti-commutative multiplication, and I plus is a Jordan algebra of bilinear form on F, on V. In this form, this bilinear form, well, V has anti-commutative product. So it has a structure of anti-commutative algebra, and the product of two vectors, say V1, V2, this a form. For instance, for Kelly algebra, it will be seven-dimensional Maltsev algebra. For quaternion, it's three-dimensional simple algebra, and so on. In general, it's some anti-commutative algebra. And also, this form is associative form. So this anti-commutative algebra, which has this form, which is associative invariant form, and so the classification of this quadratic algebra is reduced to classifications anti-commutative algebras with this form, in a sense. Well, and Kokoris algebras. I don't know about Kokoris algebras. Probably. And for Kokoris algebra, I is Kokoris is called if A plus is associative. If algebra A plus is associative algebra. So this algebra, in fact, can be considered, let's say, some B, which has this means that B with respect to dot is associative commutative algebra, and which has a bracket. An anti-commutative bracket. On B. And there is a bracket, no condition about bracket, not Lie, something, but there is a Leibniz identity. So in effect, this is a so-called generic Poisson algebra. Generic means when it is not Lie, maybe Lie, well, no, usual Poisson algebra is a Lie Poisson algebra. One can consider Maltsev Poisson algebra, etc. Depend what identity satisfies this bracket. So Kokoris algebra is equivalent to learn Kokoris algebra. It's the same as study this generic Poisson algebras. And the condition of simplicity, it means that it has no ideals which invariant under brackets. One can prove that in characteristic 0, every, well, Kokoris algebra is associative, it's commutative. Well, bracket is 0 means bracket is 0, just in characteristic 0, but in characteristic P, it's an open question. It is an open question whether there exists simple Kokoris algebra in characteristic P. Okay, I think for me it's time. Thank you very much. Just some small open questions. I think maybe it will interest you. Thank you.
Questions? Comments? So let me make a comment that it's probably not the best comment or not best formulated for YouTube for online transmission, but like, let me say it like this: I will be happy if and when I will be of you started your talk with that you are getting old and like becoming a child and child problems and so on. I will be happy to be at your age when and if at least half as fit and strong as you both physically and mathematically.
I also will be happy to see you.
Thank you. Let's thank you one again. We continue, and now very special guest as well, and for the following reason. If you look into our first seminars in 2020, Lijor, Ivan gave number 1 and Olivier gave number 3, but it's the only one which we don't have recording. Olivier did not, I mean, he did not accept the one we recorded, and he promised us he will do another one. He never did. So we are now like taking our, so we will record this one and we'll put it on a Lijor seminar page. If you admit, of course, but if you allow, but hopefully you did allow. So please, Olivier Mathieu from University of Lyon.
Yeah, first, I'm very sorry for the previous leisure seminar, but Irina should say that it was online, and it's very difficult to give seminars online. I could not feel the feedback of the audience. It's much more easy in your presence. So thank you very, very much for your presence here. And I would like to speak about linearity and non-linearity of automorphism group. Of automorphism group of the plane. Okay, I'm sorry, there was another pen. No, it was red. It was red pen. I'm sorry. Okay. 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 So first, let me explain. First, let me explain what a linear group is. So I take a group gamma, and I say that gamma is linear if gamma can be embedded into some GL and R with where R is a ring. So for me, linear means linear over a ring. And the group gamma is called linear over a field if, as you can guess, gamma can be embedded into GL and K for some integer n, of course, and some field K. So these are the main definitions. And it turns out that if you take algebraic variety, say affine algebraic variety, many authors show that the automorphism group of X shares properties with linear groups. And this has been shown by many authors. For example, there are papers by de Mazur, but also a paper by Serre about finite subgroups of the Crémonec groups, and a series of authors. And as I understood, the last series of results are due to Bezushak, Petravchuk, and Zelmanov. But I will give one specific example of such results. And this is a theorem by Stephen Lamy, and it dates back from 2000. And he says that the automorphism group of C2 satisfy Tits alternative. What Tits alternative is, it means that any subgroup either is essentially solvable, means virtually solvable, means So it has a finite index subgroup which is solvable, or it contains a free subgroup. There is nothing between. This is its alternative. And so, of course, it's a natural question to ask, but does, if you take any field, does automorphism of the plane is really linear, is non-linear? So let me explain what it is. So the automorphism of K2 is a group of all automorphisms phi, which are of the type f of xy, g of xy. So it's a pair of polynomial such that it is invertible. So the corresponding map is invertible with inverse is also polynomial. Inverse for the composition, of course. And this is a well-known group. And indeed, when I look at the literature, there was a following result due to Cornulier. It says that the automorphism group of any field of characteristic 0, but say Q for simplify, is not linear over a field. And there was a question which was, does it contains, does this out of Q2 contains a subgroup, a finitely generated subgroup. So FG means finitely generated subgroup, which is not linear. So to explain the question is clear, but let me explain the scale of linearity and non-linearity. On the top, you have groups which are linear over a field. Then you have intermediate properties, and the opposite properties is groups which contains a finitely generated subgroup which is not linear even over a ring. So you see on the top, this is the strongest form of linearity. Here, it is the strongest form of non-linearity. And between, you can guess, you can find a lot of possible variants, which are between both of them. And you say Cornelius' theorem was not linear over a field, didn't say anything about a ring. And Cornelius, even with some difficult argument, arrived to the conclusion that it was not linear over a product of fields, but he didn't go further. And so now, to explain the first result, I will need to introduce some notations. And why I make the statement a little bit more complicated will be clear later on. So I introduce first the special automorphism group of K2, which are the automorphism phi, such that the Jacobian of phi means the determinant of the differential is 1. Note that when you take the Jacobian of a polynomial automorphism, it is an invertible polynomial. It means it is a constant. Okay, and so I ask when this constant is 1. So in some sense, it is a codimension 1 subgroup. Of course, out of K2 is not really an algebraic group. It's a kind of infinite dimensional group. But you have an easy notion of what is a group of finite codimension. It means that when the quotient is a natural way, algebraic variety of given dimension. And you see these groups are functorial in K. So it is viewed as a functor. So this is a codimension 1 group. And now I introduce also other groups, which are first one is hot 0 of K2, which are all phi, such that phi of 0, of the point 0, 0, say, equal 0. It sends the origin to itself. And hot 1 of K2 are those such that phi, such that not only phi sends 0 to 0, but in addition, the differential of phi at 0 is the identity. So it means, for example, an element in hot 1 of K2 means phi is equal to xy plus some element, some terms, which are at least quadratic. Okay, so they vanish twice. They fixed 0 twice. And of course, I will set S of hot 0 of K2. This will be the intersection of the special automorphism group with hot 0 of K2. I'm sorry to introduce all these groups, but this will be important not for the theorem I state now, but later on. And my theorem is the following, theorem A. First, A1 says that if K is infinite, the field which is infinite, it means that K could have characteristic P as well. Then the special orthogonal automorphism group, which fixes 0, is not linear even over a ring. So this is the strongest form of non-linearity. And so, of course, it implies that the automorphism group is nonlinear even over a ring. That's obvious. And A2 says that if the characteristic of K is 0, then the subgroup of hot 0 of K2 contains a finitely generated subgroup gamma, which is not linear even over a ring. So it means which is the strongest form of non-linearity. Sorry, this one is not exactly the strongest form because it is infinite over characteristic P. It's not the strongest one because I don't say anything about finitely generated subgroups. But in characteristic 0, it is really as nonlinear as possible. But of course, this was more or less what we expect. If you look at Cornelius' theorem, and then you add a little bit of technical tools, and then you find it. It's not surprising. Now, I would like to come to the next theorem, which is in some sense the opposite theorem. And this theorem, in my view, is a little bit counterintuitive. Indeed, one expert, when at my preprint, say, "Oh, here you have a misprint. You want to say nonlinear," but I really want to say linear. And the theorem B, sorry, is the following. Is in some sense the opposite theorem. It says that so K is any field, finite or infinite. It says that hot 1 of K2 is linear and over a field. And the field in question is simply you add one variable to K. And this is a bit surprising because hot of K2, this one out of 1 of K2, sorry. What you have, it's very easy to prove that out of K2 is a product of the affine group of K2 times hot 1 of K2. This product means that any element can be written as a product of one element here and one element there. It's not a semi-direct product or anything like that. Just a set theoretical product, nothing more. But this one, this is an algebraic variety of dimension 6. And so it means that hot 1 of K2 has codimension 6. So you see it's a bit paradoxical because now assume for simplicity, just for a minute, if K has characteristic 0, then it means that when you take the automorphism group of K2, it contains small nonlinear subgroups, and it contains also a large linear subgroups. By small, I mean finitely generated subgroups. Indeed, one example is a subgroup with 3 generators, very simple and very small. So in some sense, it's a bit strange. And in addition of that, now for any field K, you have something even stronger than theorem B. It says that if K is big enough, then the automorphism group of K2, remember, it is a kind of infinite dimensional group, but it can be embedded into SL2 of K. And SL2 is really the smallest linear group. Means, of course, SL1, but it's not very, or GL1, but it's not very interesting. Okay. So really, it can be embedded as a very small group. And what I call big enough field, I want to say that what big enough is, big enough is not, means indeed it's not very big, it's just not too small. And the field is big enough if K is called big enough if first condition, the transcendental degree of K is at least 2. It means that K contains 2 algebraic independent elements, or it's only one of the 3 conditions, or simply the transcendental degree of K is at least 1, and characteristic of K is 0, or another possibility is the transcendental degree of K is 1, characteristic of K equal P, and when you intersect the algebraic closure of Fp with K, this is infinite. Okay, so example of big enough field. Example of big enough fields. This is very simple. There is ring, how it is called? Ring of rational function on A1 over Q. This is the first example. The second example is ring of rational function over a plane xy over a finite field, or third, the field of rational function in one variable over K, where K is an infinite subfield of the algebraic closure of Fp bar. And conversely, a big enough field, a field is big enough exactly if it contains one of the 3. So you see, it's not so big. And whenever it is satisfied, then you can embed it into SL2 Q. So now, SL2K, sorry. So now that I have theorem 2b, it's very natural to ask the following question. You take, here you have the automorphism group of K2. And here you have the automorphism group of all automorphism which fix 0/12. This is linear. This one is nonlinear. So you can ask about linearity of intermediate fields. So if gamma is an intermediate field, you can ask when does gamma linear or not? And first, it should be, there is a very easy computation which show what are the possible intermediate fields, intermediate groups. So, but gamma, so you have two possibilities. Either gamma contains the automorphism, the special automorphism group of automorphism which preserve 0, or the group gamma is of the following type. It's hot S of K2, where S is a subgroup of GL2, and hot S of K2 are all automorphism phi, such that phi of 0 equals 0, and the differential of phi at 0 belong to the group S. So, but these one are nonlinear, except if K is infinite. So the only interesting case is this one. And so, okay, you see, only these groups are interesting from this question. And the result, theorem C, is the following. So for theorem C, we will think, yeah, for theorem C, I need to define what a reducible element is. So an element G, element J in GL2K is called reducible if the eigenvalues are in K. If its eigenvalues are in K. Indeed, if one eigenvalue is in K, the second one also, of course. And now the theorem is the following. And if there is a doubt about the field, I will say K reducible. Theorem C. So you choose, let S be a subgroup of GL2. And we assume the following, one of the two, assume I. Any K irreducible element G in S is indeed unipotent. Or they assume I or II, or the other possibility. So it should assume one of the following two hypotheses. Second hypothesis is that S is finitely generated and any reducible element G in S is quasi-unipotent. Okay, quasi-unipotent means a certain power is unipotent. So it means that it means that the eigenvalues are roots of units, and here it means the eigenvalues are 1. Quasi-unipotent element of finite order, of course, is quasi-unipotent. It should not exclude this case. If one of the two conditions is satisfied, then the group hot S of K2 is linear over KT, over the field K of T. Now I would like to explain conjecture, but maybe too optimistic. But anyhow, let's state the conjecture is that hot S of K2 is linear if and only if, indeed, as I will explain later on, if this kind of group is linear, it is automatically linear over a field. But I will explain this if I have time. Is linear if and only if there is an integer n such that for any reducible element G in S, G to the n is unipotent. In some sense, the smallest power of a quasi-unipotent element, which is unipotent, can be called the quasi-order. It's not the order of the element because usually it's infinite order, but it's a quasi-order. And what you want is a bond of for the quasi-order of any reducible element G in S. And I have to say that groups which satisfy this, there are many groups which satisfy this. I mean, there are some groups which are Zariski dense in SL2, which satisfy this. If I'm not misleading, there should be, yes, of course. For example, if you take an example of group which satisfies 2 is you take SL to Z or GL to Z. It does not matter. Because if you take SL to Z, then any unipotent element has quasi-order 2, because the eigenvalue can be only 1 or -1. So, and you see this group is quite small. It's quite big. It's already Zariski-Dance in SL2. So you have some relatively big group, both S of K2, which are linear over a field. I would like to say a few words about proofs, but before that, I was sure that Ivan will ask a question. So I will answer the question of Ivan even before. Now he's a little bit sleeping, but even if he gets up, the question will be answered in advance. And why I believe that Ivan will have a question? Because there is we can ask if this phenomenon of linearity are special to dimension 2 or could be extended for higher dimension. And so we should look for what is analogous out of K2 for bigger dimension. And indeed, here I will stop at dimension 3 because for our purpose, this will be enough. So now you have, of course, you can say that automorphism of K3 is analogous to automorphism of K2 in dimension 2. But there is another possibility, which is the group of tame automorphism. And what is a tame automorphism of K2 is a subgroup which is generated by affine transformation of K3 and triangular automorphism. And what a triangular automorphism is an automorphism which sends X, Y, Z to X, Y plus some polynomial in X, Z plus a polynomial in X, Y. And in dimension 2, you can define also triangular automorphism. You simply forgot the last component. And it is well known that all automorphisms in dimension 2 are tame, generated by this transform. But there is a theorem by Shestakov and Urmibaev, very famous theorem, which says that the tame automorphism group of K3 is strictly inside the automorphism group of K3. Okay? So when you take the automorphism group of K3, you have even smaller subgroups. And so we can ask, of course, linearity for tame or linearity in general. And now let's define for K, any integer K, bigger or equal than 0, let's define term of automorphism group of K3. These are all phi, all automorphism T of how it is called term automorphism, such that phi is equal to x, y, phi, send x, y, z to x, y, z plus terms of order at least k plus 1. Okay. So there are term automorphisms which fix the point 0 k time. And the result is the following. Is that for any k, for any small integer k, and any field out k of k3 is not linear, even over a ring. So it means that the fact that out of K2 contains big subgroups which are linear is very special to dimension 2. And now that I mentioned this theorem, I forgot to mention one corollary of theorem C, not of this, which was the following. You remember that I prove that when K is infinite, the automorphism group of K2 is not linear. But here the corollary is that the automorphism group of K2 is linear over field K of T if K is finite. Indeed, it's obvious, because when you take the subgroup out 1 of K2, it is a finite index subgroup. So if you have a finite index subgroup which is linear, the group itself is linear. It simply corresponds with inducing a representation. So that's obvious. And the second corollary is that if any is that out of FP bar, when you take the infinite field FP bar, this is not linear. We already see that. But any finitely generated subgroup is linear. Because any finitely generated subgroup simply has coefficient in a finite field. So it lives inside the out of some finite field. And so this group, you see, so this group is not linear, non-linear even over a ring. Okay, but the point that this group is a kind of intermediate level of non-linearity, because is himself non-linear, but finitely generated subgroups are linear. And the big question is the following, is that if the characteristic of K is finite, say equal P, then say does the automorphism group of K2 And of course, we'll say that the transcendental degree of K will be bigger than 1, otherwise we are here, contains finitely generated subgroups which are not linear. And this is a question which is not solved. I don't know how to solve it, except for this field, of course, and of course infinite subfields of FP bar. But when the field contains transcendental element, I don't know the solution of that. But yeah. So now I explain the result, but I would like to explain a few points about the proof. I think I have 15 minutes again. Is that correct? Okay, because we start a little bit late. Thank you. So now I would like to explain 2 points about the proof. And the first point of the proof is the following. Is linearity against linearity over a field. And I found a class of groups which are linear over a field whenever they are linear over a ring. And I will describe this class of groups. And that's why in all my statements, the groups are either non-linear over a ring, even over a ring, or linear already over a field. There is nothing between. And the statement is the following. First, we need to define what an amalgamated products are. So you take G1, G2, 2 groups, and say, and a group A, and the third group A, with map F1 to G, and a second map F2 to G1 to G2, okay? Map like this. And you assume, for simplicity, that F1, F2, injective. So basically, you have 2 groups which share a common subgroup A. And you define the amalgamated product, G1, G2, amalgamated product G1, G2 over A. This is very simple. It is a product, the free product of G1 by G2 modulo the invariant subgroup modulo the following relation F1 of A equal F2 of A. Okay, maybe it's not the standard way to write relations. Usually the expert in the field write F1 of A times F2 minus 1 of A. And they don't say equal 1. But I think this is clear. It means that I said by force that the 2 embeddings should correspond to the same element in the product. This is what is called an amalgamated product. And now I say that this product is non-trivial yeah, simply means that A. So now you consider less formally that A is a common subgroup of G1 and G2, and I want that A is not equal to G1 and A is not equal to G2. Because you know, if one of the two group, G1 or G2, A is equal to A, then this amalgamated product is simply the other group. It's not interesting at all. And I introduce the following condition H is the following. For any element A in A, which is different from 1, there is an element gamma in the amalgamated product G1 star the following trick. So I defined, say, G, so I take a field K, I take GL to, sorry. Oh, sorry. I need, sorry, I changed my notation. Before I put an index, but it was a mistake. I take, this is a 2x2 matrices, which are invertible and with coefficient in the polynomial ring K of Z. And this contains the subgroup GL1 to KZ. And this is simply all phi in GL to KZ, such that 5 of 0 is the identity. Okay, you take, because you have matrices with value are polynomial, so you can evaluate these matrices at 0, and you want to get the identity. And of course, this is a subgroup of SL2 K of Z. But anyhow, now the result is the following. Proposition. And this proposition is quite easy. It's based on the theory of, Tits in the 90s, and partially also myself, built some Kac-Moody groups associated with Kac-Moody algebra. And if you apply this for SL2, you immediately, you know how to describe this kind of groups, and you can realize that very easily that the automorphism group of K2 is indeed isomorphic with GL1 to KZ. But we have to be careful. We have to be careful. This isomorphism is not canonical. For example, if you look at any element here, it can be written as a product of triangular transformation, but twisted, but conjugate by GL2. And assume that here you take an element of the form E1, En, with the degree of EI equal Ni. And then the corresponding here is something which has degree. So the total degree, the degree of the transformation is N1, NL is a product of Ni. It means it is a map which sends XZ to f of xy, g of xy, and one of the two or both have degree N1 and L, the maximal degree of f and g. But the corresponding element, the corresponding transformation has degree N1, as degree N1 plus NL minus L. So you see, it is a map which does not preserve at all the degree. And the degree of a transformation like this is very easy to describe. You choose, it's a 2x2 matrix. So you take the maximal degree of the 4 entries. Okay, so it does not preserve at all the degree. And of course, there is no explicit formula. The only exception may be, but there is a canonical way. Usually, there is no canonical way to write this isomorphism. I know to prove that there is some, but no way to prove that there is something canonical. The only case where there is a canonical isomorphism is for a field K of characteristic 2, and which is perfect. So for this one, we have a kind of canonical formula, but which is not explicit. But there is a canonical choice only in this case. So it's a very restricted case. Okay, and of course, this one is a linear group. It's inside GL2 over the field K of Z. So that's the trick. Now, if I have a little bit of time, one second. Now, you can define GL S to KZ to be all phi, transformation phi, such that phi of 0 belongs to S. And GL S to K of Z is the semi-direct product of S by GL1 to KZ, of course. That's obvious. And in the same way, the automorphism S of K2 is a semi-direct product of S by OT1 of K2. And of course, it's very tempting to expect that the two groups are isomorphic, but it is not the case. But the trick is that if all reducible elements in G in S are unipotent, then the two groups are isomorphic. And OT S is isomorphic to GLS. By OT S, I mean this one. By GLS, I mean this one. And so it is linear. And when S is finitely generated, the trick, very easy trick, is that S contains a subgroup of finite index for which all reducible elements are unipotent, and therefore it is linear. That's the trick. But that's very amusing because you see, when you take the group of linear automorphism which sends 0 to 0, it is an extension of two linear groups. It's a semi-direct product of two linear groups, very simple groups, but it is not linear itself. Because the way to make the semi-direct product is different, of course. So now I finish, and I thank you very much for your attention.
Any questions or probably comment for some already answered questions? Olivier, you wanted to make a comment? You? No. You told me that you probably would like to comment on. That was it.
I would like to congratulate Ivan for his birthday. And just as you see, I mentioned one of his beautiful work with Urmi Baef on the T automorphism group of K3. So that's my comment. But I could not, I prefer not to speak about this at the beginning because I don't want to spoil the end of the story.
Thank you. So we are finishing with our transmission to Lijor, and we will continue our session in 25 minutes, like half an hour, right? And now we continue to coffee break, and then Sasha will talk. So thank you, Lijor. And yeah, we finally got our recording of Olivier talk 2 years later. Let's thank both of speakers.
you.